Definition and working principle. Insertion sort is a simple comparison-based sorting algorithm that builds the final sorted array one element at a time. Imagine a hand of playing cards. You keep the cards you have already sorted in your left hand and insert each new card from the deck into its correct position in that hand. The algorithm scans the already sorted part from right to left, shifting larger elements one position to the right until it finds the right spot for the current key. Pseudocode using zero-based indexing. Insertion sort a 0 to n-1. For I equals 1 to n-1 do. I is the index of the element to insert. K equals a I store the element to be placed. J equals I-1. Start comparing with the element just before I. While j greater than or equal to 0 and a j greater than chi do. A j plus 1 equals a j shift larger element to the right. J equals j minus 1. Zend while. A j plus 1 equals key, place key into its correct position. Zend for. Sort the numeric array equals 5, 2, 9, 1, 5, 6. I equals 1, key equals 2. Compare with a 0 equals 5, 5 greater than 2. Shift 5 right, resulting array 5, 5, 9, 1, 5, 6. J becomes minus 1 stop. Insert key at a 0, resulting array 2, 5, 9, 1, 5, 6. I equals 2, key equals 9. Compare with a 1 equals 5, 5 greater than 9, no shift. Insert at a 2 already there. Array unchanged 2, 5, 9, 1, 5, 6. I equals 3, key equals 1. Compare a 2 equals 9 greater than 1 shift, resulting array 2, 5, 9, 9, 5, 6. Compare a 1 equals 5 greater than 1 shift, resulting array 2, 5, 5, 9, 5, 6. Compare a 0 equals 2 greater than 1 shift, resulting array 2, 2, 5, 9, 5, 6. J equals minus 1, insert key at a 0, resulting array 1, 2, 5, 9, 5, 6. I equals 4, key equals 5. Compare a 3 equals 9 greater than 5 shift, resulting array 1, 2, 5, 9, 9, 6. Compare a 2 equals 5 greater than 5, no equal stability keeps order. Insert at a 3, resulting array 1, 2, 5, 5, 9, 6. I equals 5, key equals 6. Compare a 4 equals 9 greater than 6 shift, resulting array 1, 2, 5, 5, 9, 9. Compare a 3 equals 5 greater than 6. No. Insert at a 4, resulting array 1, 2, 5, 5, 6, 9. Final sorted array 1, 2, 5, 5, 6, 9. Each iteration inserts the key into the already sorted prefix a 0 to I-1. Time complexity analysis. Let T of n be the total number of primitive operations, comparisons plus moves, for an input of size n. Worst case, array sorted in descending order. The inner loop runs I times for each I from 1 to n-1. T sub worst of n equals the sum from I equals 1 to n-1 of I, which equals n-1 times n over 2, which is theta of n squared. Recurrence form, T of n equals T of n-1 plus theta of n, with T of 1 equals theta of 1. Solving gives T of n equals theta of n squared. Best case already sorted, that is ascending order. The inner while condition fails immediately each time, so only one comparison per outer iteration. T sub best of n equals theta of n. Recurrence, T of n equals T of n-1 plus theta of 1, which gives T of n equals theta of n. Average case random permutation. On average, the key is larger than half of the elements in the sorted prefix, so the inner loop runs I divided by 2 steps. T sub average of n equals the sum from I equals 1 to n-1 of I divided by 2, which equals 1/2 times n-1 times n over 2, which is theta of n squared. Hence average time is also theta of n squared. A summary. Best big O of n. Average big O of n squared. Worst big O of n squared. The quadratic behavior stems from the nested loop structure, while the linear best case appears because the inner loop can terminate early. Space complexity evaluation and in-place property. Insertion sort uses only a constant amount of extra storage. One variable k to hold the element being inserted. One index variable j for the inner loop. All rearrangements happen inside the original array moving elements by assignment. Therefore, space complexity equals theta of 1 constant. This makes the algorithm in place. It does not require an auxiliary array of size n. Proof of correctness and stability. Loop invariant. At the start of each outer loop iteration I, for I greater than or equal to 1, the subarray a sub 0 to I minus 1 is sorted in non-decreasing order and contains exactly the same elements as the original prefix. Initialization I equals 1. A sub 0 is a single element trivially sorted. Maintenance, the inner loop inserts key equals a sub I into its correct position within the sorted prefix by shifting larger elements rightward. After insertion, the prefix a sub 0 to I is sorted and contains the same elements as before. Termination, I equals n. The invariant tells us that a sub 0 to n minus 1, the whole array, is sorted. Stability, the algorithm only moves elements strictly greater than key. When a sub j equals key, the while condition a sub j greater than key fails, so the equal element stays to the left of the new key. Hence, the relative order of equal keys is preserved, and the sort is stable. Explanation: comparison with selection sort and bubble sort exam focused. Basic idea: insert each element into sorted prefix. Repeatedly select the minimum from unsorted part and swap to front. Repeatedly swap adjacent out-of-order pairs, bubbling larger elements to the end. Number of swaps: at most n-1 swaps 1 per outer iteration. Exactly n-1 swaps 1 per iteration. Up to theta, n squared swaps. Every comparison may cause a swap. Comparisons: worst: theta n squared, theta n squared, theta n squared. Best case time: big O of n already sorted. Theta n squared still scans whole array. Big O of n if optimized with a flag that stops early. Stability: stable does not reorder equal keys. Not stable swap may move equal elements. Stable adjacent swaps keep order. When exam expects answer: small or nearly sorted inputs as a subroutine in hybrid sorts. When you need a simple algorithm with few swaps regardless of input order. To illustrate concept of repeated passes often used for teaching swaps. Key takeaway for exams: insertion sort shines when the data is almost sorted because its inner loop terminates early, giving linear time. Binary insertion sort. Standard insertion sort finds the insertion position by a linear scan, O of I for the ith element. Binary insertion sort replaces this scan with a binary search on the already sorted prefix. Binary insertion sort of a sub 0 to n-1. For I from 1 to n-1 do. Key equals a sub I. Binary search for the index pose where key belongs in a 0 to I-1. Low equals 0, high equals I-1. While low is less than or equal to high do. Mid equals low plus high divided by 2. If a sub mid greater than k, then high equals mid minus 1, else low equals mid plus 1. Zend while. Pose equals low insertion point. Shift elements right to make room. For j from I-1 down to pose do. A sub j plus 1 equals a sub j. Zend for. A sub pose equals key. Zend for. Comparisons. Binary search uses floor log base 2 of I plus 1 comparisons per iteration, total theta of n log n comparisons. Movements shifting still requires up to I assignments, giving theta of n squared moves. Overall time remains theta of n squared because moves dominate, but the algorithm reduces the number of comparisons, which can be beneficial when comparison is expensive, for example string comparison. Trace the algorithm on the array 4, 3, 2, 1. Write down the array after each outer loop iteration and count the total number of comparisons and swaps. Expected answer: after each pass the prefix 1, 1, 2, 1, 2, 3, 1, 2, 3, 4. Comparisons equals 1 plus 2 plus 3 equals 6. Swaps equals 3, 1 per insertion. Complexity calculation for an input that is already sorted. Show why the runtime is theta of n. Explain that the inner while condition fails immediately, giving 1 comparison per iteration. Edge case handling: what does the algorithm return for an empty array or a single element array? It returns the array unchanged. Loops do not execute. Stability check: given the list of pairs 5A, 3B, 5C, run insertion sort on the numeric key. Show final order and argue why it appears before C. Binary versus linear. For n equals 8, compute exact number of comparisons for standard insertion sort worst case versus binary insertion sort. Standard 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 equals 28 comparisons. Binary, floor log base 2 of 1 plus floor log base 2 of 2 plus floor log base 2 of 7 equals 0 plus 1 plus 1 plus 2 plus 2 plus 2 plus 2 equals 10 comparisons. Advantages, limitations, and when to prefer. Advantages. Simple to understand and implement. In place O of 1 extra space. Stable, preserves order of equal elements. Excellent performance on small, n less than or equal to 20 to 30, or nearly sorted data, best case O of n. Acts as a useful subroutine in hybrid algorithms. For example, TimSort uses insertion sort for small runs. Limitations. Quadratic worst case makes it unsuitable for large, randomly ordered arrays. Number of element moves can be high shifts, even if comparisons are reduced by binary search. Not cache-friendly compared to more advanced sorts like quicksort or mergesort for big data. When to prefer in an exam. The problem states that n is small, less than or equal to 30, or the input is almost sorted. You are asked to prove stability or demonstrate a loop invariant. Insertion sort's simple structure makes formal proofs easy. The question asks for a space-optimal solution. Insertion sort's O of 1 extra space is a clear answer. If the exam includes a hybrid algorithm design, for example, use insertion sort for the first 10 elements, you can justify the choice based on the above strengths. In summary, think of insertion sort as the hand of cards technique, perfect for a small deck or for tidying up a deck that is already almost in order.